So I like to stick to the schedule. All right, some of these are going to look familiar, but I want to emphasize the fact that
Good question. Is Anderson the first one you're gonna be able to get that from panel?
I don't know. It might not even look like that. That's what I was about to say. We're going to go over these types of questions, and you need to be thinking, how could my sneaky instructor change this question to make it slightly different? That way, you need to read the question and see what the question is asking for. Because if I change what it's asking for and it looks like something you've seen before, you may put the wrong answer in there. Okay. So let's go. Number one, which of the following is an example of a quantitative observation? The difference between quantitative. Just think quantity, that's numbers. That implies numbers. And qualitative is the other possibility. And that implies appearance. Just a general appearance or comparisons. Like that board's longer than that board. That's qualitative. Or the sky is blue. Now, if I said the sky is blue because it absorbs light at such and such a wavelength, then that would be quantitative, because it would have a number associated with it. Now, to answer this question, which one of these is an example of a quantitative? Well, I just told you one of them. A is qualitative. Solution 1 is darker than 2. That's qualitative, right? Liquid in beaker A is blue. There's another one. Temperature of the liquid is 60 degrees Celsius. That's it. Bingo. So D is the only one that would answer that question. All right. How about number 2? Well, I'm just going to smear it. Let's do this. A little more work, but gives you better cleaner board. Which of the following figures represents a result having high precision? It might be more than one of them. So the difference between precision, what's the other one? Yeah, accuracy. In order to be accurate, you have to know what the true value is or the accepted value. Then any measurement you make that comes close to that would be considered accurate. Now, close, that's operationally defined. Usually within 5% is considered close. But to do this one, you have to know a true value or an accepted value. With precision, it doesn't matter. Precision, all you need is 2 or more measurements that are in agreement. And that also is operationally defined. If their spread is plus or minus 2.5%, say within 5% of the middle, then you would be considered precise. So based on these pictures, the one that's precise is one that has a close grouping, right? Roman numeral 2 is a good example. Roman numeral 3 is also a good example. So 2 and 3 would be, E would be the best answer for that one. What else do we know about these? Let's say number 2. Is that one accurate? No. None of those measurements, nor the average, is close to the bullseye. So 2 is not accurate. It's precise, but not accurate. Number 3 is the ideal. It's both accurate and precise. And then, of course, number 1 is definitely not precise. Is the average of those accurate? I don't think so. If you look at if you connect the lines, say connect upper right and lower left, and then connect to lower left and upper left and lower right, and where they cross is not on the bullseye. And the one that was left out is not on the bullseye either. So that one is neither accurate nor precise. Okay. Now, if you had one with 4 or 5 target hits, and you could visualize an average value that's on the bullseye, then you would say that that would be accurate but not precise. And that's what we get a lot in especially in field research, where the environmental conditions just throw your numbers all over the place. So as a consequence, it takes us a minimum of 3 years. It took me 5 years of field research to get a data set that was presentable. If you have more controlled conditions, like in a greenhouse, or even better in a growth chamber, then you can get your results in just one planting. But in this case, if you want quick results, don't go into agriculture. Okay, number 3. The amount of uncertainty in a measured quantity is determined by 2 things generally go into determining how good your numbers are in a measurement. One is the instrumentation. If you have good instrumentation, and that generally scales with cost. The better your instruments, the more costly they are. And they tend to go like this. You can get, for a little bit of increase in cost, you can get, actually, should be the other way. It should be like this. For an increase in cost, you get a very good return on your investment. But when you get up, the more and more it costs, the less and less you return. So I digress. Instrumentation definitely is a clue. And then who's operating it? Right? If a person, like if I spent, or my employer spent a couple of $100,000 on a diagnostic piece of equipment for an automobile, and I knew how to plug it in, I know where the place is that you can plug it in. And then it spits out these numbers, and I don't have a clue what they mean. You know, what does this mean? What needs to be repaired? So the operator in that case is clueless. And it doesn't matter how good your instrument is, you're not going to get a repaired auto. So you need both the instrument and the operator to be competent, trained, competent. And that would be the observer and the measuring instrument are the 2 limiting factors in any measurement. The boiling of water is, well, let's see here. Okay, physical change, chemical change, and then there's a qualifier after it. So first of all, let's eliminate, let's narrow it down. Is that boiling water, does it involve a physical change or a chemical change? Physical, right? Because the identity of water does not change in the process. Okay, so we know it's physical. Now to narrow it down, which one of these is correct about why it's physical? Physical change because the water merely disappears? Well, if that was your only choice, then yeah, I'd go for it. But you do have a better choice. Physical change because the gaseous water is chemically the same as liquid water. So that would be B, wouldn't it? All right. Let's see, number 5. Okay, definition time. What's a solution? A solution is a homogeneous mixture of two or more substances. And when we say mixture, that means that those substances still retain their identity in the mixture. And they can be separated by physical means. And homogeneous means uniform throughout. The composition or the percent composition of each of the components is identical no matter where you sample it in the total. So A would be a good example. A would be good for that. Homogeneous mixture. It's another word for solution. Okay. 6. Which of the following has a different value on the moon compared to the Earth? I know you've seen this one before. All right, what's constant throughout the universe? Well, under most circumstances. Mass, yeah. Even time. As long as you don't get close to a black hole, you're good with your time. And you're not moving close to the speed of light, right? Then all bets are off. Then you have to turn to relativity. But mass is constant, time is constant. Moles are constant because they're just counting. They're just numbers of things, right? So the only one that really changes when you move from one large mass to another large mass is weight. Weight is an expression of force. It's related to mass, but it's also related to the gravitational field. If the field is stronger, then there's going to be more force applied at the surface of that object. And that's where weight comes in. Okay. About 7. All the following are true, except. All right. Ions are formed by adding electrons to a neutral atom. Well, that's true. You can form an ion by adding electrons. Ions are formed by changing the number of protons in an atom's nucleus. I don't think so. What do you get when you change the number of protons? You get a different element. Yeah, right. So we know that was false. That was B, wasn't it? B is definitely false. Ions are formed by removing electrons from a neutral. Yeah. The only way you can make an ion is to diddle with the electrons. It can have positive or negative charge. That's true. Metals tend to form positive ions. Is that true? Yeah. Metals tend to lose electrons. They prefer that. How about non-metals? What do they like to do? Just the opposite. They want to gain electrons. So if I slid one in there and says metals tend to form negative ions, that would not be true. Then I'd have to change B to be true. Right? Okay, that's how that works. All right, number 8. All the following are characteristics of metals except. Okay, they're good conductors of heat. Oh yeah, very good conductors of heat. Malleable, as a general rule, yeah. Except for the liquids, right? There's only one of those, right? At room temperature. Mercury. Ductile. What does ductile mean? It means they can be stretched into wires, thin wires. Often lustrous. They are if you polish them. If you deposit from a chemical reaction, say you deposit silver on the inside of a glass bulb like they do for Christmas ornaments, then at first it comes off black. It's only when you get a complete sheen of silver on the inside of that it turns lustrous. But initially it's black. But yeah, they're often, that's why we say often lustrous. That gives us an out. And they tend to gain electrons in chemical reactions. No, they tend to lose electrons. chemical reactions. So that's E. That's the bad one. Which of the following is paired incorrectly? Now we're getting into nomenclature when we learned how to name compounds and identify whether they were weak or strong in chemical terms. Okay, so if we have an acid, what do you need? You need at least one of these, right? At the beginning. You can have more than one, but one is it, absolutely. And then something else. Okay. If we're going to name a base, then most often you have something here and then at least one of those. Especially if it's an Arrhenius base. If you have a Bronsted-Lowry base, then you need a compound that will accept protons. Our best example of that one is ammonia. Okay, so that's a base. This is a base. That's an acid. Okay, so when we look at our examples here, we want to pair them up as acid base, and then are they strong or weak? So if we look at each one of them, then A is H2SO4. Anybody got a name for that one? H2SO4. We're going to do a little nomenclature at the same time. When you have something like this, you have a polyatomic ion here. There's an oxygen in it, so we don't say hydro. But this is derived from the polyatomic ion sulfate. And H become X. So we say sulfuric acid. That's an acid. Is it strong or weak? It's strong, right? Well, technically, it's strong for the first hydrogen. It's weak for the second hydrogen, but to simplify things, it's considered a strong acid. How about HNO3? How would we name that one? Similarly, nitrate, nitric acid. Right. Is that one strong? Yes. So that's the wrong one, because that says weak acid. It's not, it's strong acid. This is also, this would be barium hydroxide, right? Hydroxide is a polyatomic ion, OH minus. Barium is an alkali metal, alkaline earth, so it has a 2+ charge. So we need 2 of these to match that one. And then this one, now we don't have an oxygen. So we start with hydro. And actually, if this were a gas, we would name it hydrogen chloride. But if we're going to name it as an acid in aqueous solution, the chloride becomes ic, hydrochloric acid. And that one is strong. Oh, by the way, this one is also strong. Alkaline metals and alkaline earths bases are strong. They don't all have good solubility. But if they have low solubility, then whatever goes into solution is completely dissociated. And that makes them strong in the chemical sense. And then the last one is ammonia. That's a base. Right? And it has a grandfathered name. Instead of naming it nitrogen trihydride, it's ammonia. And ammonia is a weak base. Okay, so all those are correct except for that one. Well, that's correct, but the way it's written there is not correct. All right. Let's see. Number 10. Which of the following is correctly paired? All right, symbols for named measurements. Is the first one correct? Yeah. Lambda is wavelength. That's wavelength. Second one, frequency. It looks like a V, but it's really a Greek letter nu. Right? Sometimes you'll, to avoid confusion for students that don't catch on to Greek very well, sometimes they'll do that and say that's frequency. But we've been using the Greek letter. Speed of light. See? Yeah. C is reserved for speed of light. Hertz. Is that the correct measurement for hertz? Reciprocal seconds. That's correct. And the shortest, following is incorrectly paired. The shortest wavelength, X-rays. You know what? Oh no. X-rays have the next to the shortest wavelength. Right. Shortest wavelength is gamma. Gamma rays are the shortest wavelength. The shortest wavelength implies the shorter the wavelength or the higher the frequency, the higher the energy. And gamma rays are the most energetic electromagnetic part of the spectrum. Right, so that's the bad one right there. Close, but no cigar. All right, number 11. Let's see. Consider the following portion of the energy level diagram of hydrogen. So at n equals 1, that position, that quantum level is minus 2.178 times 10 to the minus 18 joules. Notice we get more and more negative as you get closer to the nucleus because you're getting lower and lower in energy. Closer. It takes more energy to get to the outer layers. And how much energy is assigned to infinity? 0. Once you get to 0, you're at infinity. That electron is free from the atom. Okay, so for which of the following transitions does the light emitted have the longest wavelength? Okay, so this question has a bunch of blue smoke in it. You don't need to know those values to answer this question. Which transition gives you the longest wavelength? The longest wavelength equals the lowest energy or the smallest frequency. And to get that, you need the lowest energy needs the smallest transition. So if you have level 1, 2, 3, 4, like that. The smallest transition is going to be between 4 and 3. If you're looking at emitted light, the electron comes from out here in. So if we go from 4 to 1, C would be actually the highest energy. The lowest energy would be 4 to 3. Hear that short jump right there. That would be the lowest energy. A. Highest energy would be 4 to 1 of our examples. All right. Which of the following statements best describes the Heisenberg uncertainty principle? Werner Heisenberg said that For small objects, like on the atomic or subatomic level, you cannot know both the position and momentum, which is mass times velocity. You can't know both of those with certainty. If you know one with certainty, the other one is uncertain. You can only say maybe say a region. So since we're more interested in energy for subatomic particles, and particularly electrons, we focus on this one. And we get this one nailed down pretty good. That lets this one, give us a region. And I think it was, let's see, is it less than or equal to or greater than or equal to? Look on the last page. Does it have it on useful information? Let's see. No, I don't see it either. All right, let me get back up to 12. Well, let's see which one makes sense. It's going to be H over 4 pi, I think is the partly formula. Let's see, does that make sense? This has to be less than that. So if this is really big, that can be small. I think that's it. Less than or equal to. Anyway, which one of these puts that into a single sentence? Impossible to accurately know both the exact location and the momentum of a particle at C. Which of the following is an incorrect designation for an atomic orbital? All right, so if we're gonna, let's do a little review. Principal quantum number, angular momentum quantum number, magnetic quantum number, and spin quantum number. So this one can be anything from 1 to on up. This one can be 0, 1, 2, up to n minus 1. Okay. This one can be minus L, 0 to plus L in whole number increments. And this one can be either plus 1/2 or minus 1/2. Okay, what does N mean? It references energy and size. How about this is principal quantum number. Let's just be complete. That's principal. This is angular momentum quantum number, and that references shape. Okay. This is magnetic. Magnetic quantum number. And this references orientation. Which direction is it pointing? And this, of course, is spin. Okay. So if we take each one in order, A, B, C, D, E, right? First one is 1s. Is that allowed? Well, first of all, what is an S? That references the angular momentum. This is S, P, D. Let's go ahead and put this one in, and F. That's all the ones you normally need. So can we have an S with a principal of 1? Yeah, right. Have 1, and then you can have that one. That's it. That's all you can have, actually. That one's okay. How about B? 3D. 3D. So if we have 3 up here, we could have 0, 1, or 2. Yep, that's good. How about C? 1P. Nope. You have 1, 0. That's it. Oh, wait a minute. Where'd P come from? I don't know what P is. P's looking down here. Yeah. You would have to get, oh, there's P. Duh. Can't have it though. And then 4F, obviously. All right, if we get to 4, we can have 0, 1, 2, and 3. We're good there. And to be complete, 6S. You can have S with any principal quantum number. Okay, so the bad one is C. Um, 14. Which of the following was not an elemental property usually predicted by Mendeleev for as yet elements? All right. He used physical and chemical properties to group elements. So boiling point, density, oxide formulation, those are all good. Atomic mass as they knew it. Yeah, that was good. They had no idea about electron configuration at that time in the mid 19th century. Right, so A, electron configuration is the one that he couldn't possibly have used. All right, 15. Which of the following atoms has 3 electrons in p orbitals in its valence shell? 3 electrons in p orbitals. Oh, I forgot that part. What we typically call this is a shell. This is a subshell. This is orbital. Okay, 3 electrons in the p orbitals in its valence shell. Right, so we can use the periodic table to answer that question. If it has 3 electrons in its p orbital, that means we're over on this right-hand side of the representative elements. And we just count over 3. Boron, carbon, nitrogen. So we're looking at the pnictogens. Do we have pnictogen in that group? No. Barium, gallium, no. Gallium? No, that's only 1 electron. Vanadium? No, that's a transition metal. Bismuth? There it is. Bismuth. 3 electrons in its valence shell. That's where understanding how the periodic table is constructed will answer that question for you quickly. Right. Let's see. Oh, 16. Go. force between two bodies having identical electric charges. So that could be either two negatives or two positives. What kind of force are they going to experience? Yeah. And it's going to send them off in opposite directions. Unless you apply an equal and opposite force to push them together. And if you do, if you try to push them closer together, you're storing up potential energy in that electric field. As you force them close together, they're going to resist. And to get that energy back, you just turn them loose. Okay, so that would be A, force of repulsion. B would not satisfy. You don't get repulsion when you have one negative and one positive. Or actually, the error there is you get identical charges. If they're both negative, it says they're repulsive. If they're positive, they're attractive. No, only opposites attract in that world. Okay, 17. Which of the following has 61 neutrons? Let's see. 61 neutrons. 47 protons. Okay. And 46 electrons. So if this is the number of protons and you have 46 electrons, what's the charge? It's positive 1. So this value up here is going to be 108. So what's got 47 and 108? Well, we look at 47. That's silver. Okay. So we got silver. 47, 108 with a positive charge. And B. We threw that E in there just to see if you're paying attention. Right. E would be neutral silver. B is the ion. In fact, that's the preferred ionic state of silver in a compound. It's a single charge, single positive charge. All right, 18. A little nomenclature here. In aqueous solution, which is incorrectly named. All right, we did some of these already. That first one is sulfuric acid. That one's correct. How about B? H2CO3. So we look at this carbonate, carbonic acid. Is that it? Yep, that one's good. H3PO4. Phosphate. Phosphoric acid. That one's correct. HCN. In aqueous solution, that would be hydrogen cyanide. With H, we have hydro, because there's no oxygen. Cyanide becomes ic, cyanic acid. Is that correct? No, that's the wrong. So that's the one we're looking for. And then we did HCl already, it's hydrochloric. All right, number 19. So to work number 19, I got a little picture there. Help us. A manometer is attached to a sample of gas that occupies a volume of 2.34 liters. All right, so we got the 2.34 liters here of gas. It's attached to a manometer, and the manometer looks like this, like that, open to the atmosphere. That. Okay. The mercury level in the arm of the manometer attached to the gas sample is 24.3 tore lower than that, the arm open to the atmosphere. So the difference between here and here is 24.3 tore. Okay, so what does that mean? That means that the pressure inside this vessel is higher than the atmospheric pressure. Are we given that also? Atmospheric pressure is 1.23 atmospheres. So bearing down here is 1.23 atmospheres. Okay. So there's enough pressure in here to balance both that pressure plus that difference right there. What's the pressure of the sample of gas? All right, we got apples and oranges here. So since the answers are all given in torr, we ought to convert this one to torr. So you want 1.23 torr, dimensional analysis. So how many torr per atmosphere? 760. Right. Oh. My own worst enemy. Let's try that again. Atmosphere on the bottom, or on the top. There we go. That looks much more better. Okay, you got a number for me? Or did you just add them all together? Oh, you didn't do it already? Oh. You what? All right. So 1.23 times 760 is 934.8 torr. Atmospheres cancel, leaves 4. And then it also has to balance this much. So 24.3 is 959.14 is the pressure inside that vessel. Nearest answer to that one is E. Okay, pick the best answer. Next, 20. Consider a gas in a 1 liter bulb at STP that is connected by a valve to a bulb that is initially evacuated. Okay, so we have 1 liter here. And at standard temperature and pressure. We'll fill that in a minute. And we got a valve here connecting it to another one, and we don't know what size that one is, but it's a vacuum. So we know what's going to happen when we open that valve. It's going to go right until the pressure is equalized. What occurs when the valve between the two bulbs is opened? What's true about the value of delta H? All right. So the question is about delta H. Right? What's the change in enthalpy? All right. If STP is maintained, delta H has to be 0 because the temperature is not going to change. And that's the only way that you can detect enthalpy, change in heat. So it's equal to 0. While we're at it, let's see. What is, let's see, what's the other one? Delta E, right? That's equal to, excuse me, not G, Q. Q plus W. Well, we know Q is 0 because delta H is 0. How about W? Was any work done? Nope, not a bit of work. So that one's also 0. Let's see, what else did we do? Well, we have these separate in one answer. How about this one? Entropy. What's the change in entropy? Greater than zero. You get more entropy when this moves into a larger volume because you increase the number of microstates. We've talked about that, haven't we? Where's that next semester? Oh, sorry. I'm giving away the store. Never mind. Right. Entropy's next. Okay. Little taste of the future. 21. In which group do all the elements have the same number of valence electrons? All right, so all we need to do here, for simplicity's sake, and E is none of those, so none of them have the same number of valence electrons, is go to the periodic table. Right? This one has a halogen in it. Phosphorus and sulfur are not halogens. Right? So that one's out. B, silver, cadmium, argon is a noble gas. Neither one of those others is a noble gas. Right? So we know their valence electrons aren't the same. Sodium is an alkali metal. Calcium and barium, yeah, are alkaline earths, right? So they don't have the same number of valence electrons. Phosphorus, arsenic, selenium. Phosphorus and arsenic are good, but selenium's next door. It has a different number, right? So none of them. Now, let's say, what if I said phosphorus, arsenic, and antimony? Yeah. Just think like a sneaky instructor would think. And be prepared. Let's see, 22. The ground state electron configuration of selenium. Okay. Selenium. And we're allowed to use the abbreviated form. That's good. Selenium has 34 protons, 34 electrons. So we back up until we reach the next noble gas, which is argon. So we take argon as our core at 18. And then we go from argon down to fourth period. 4s2 gives us potassium and calcium. Then we move across the 3Ds, 3D10s. Then we get to the zinc and gallium. Yeah, gallium, germanium, arsenic, selenium. That's 4 electrons in the 4p. There's your configuration. Which would be A. Okay. So periodic table, good. Doing it the long way, bad. Not bad. Less convenient. And we want easy when we can get it. Okay, 23. Which of the following bonds would be the most polar without being considered ionic? Okay, so let's put all these up here. D and E. Yeah. Okay, so we got this bond, this bond, this bond, this bond, this bond. All right, we got any without being considered ionic? We got any ionics in here? Definitely that one. That's ionic. Non-metal, 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 non-metal. Silicon's considered a non-metal. It's a metalloid. So we're probably going to have to leave that one alone. And then non-metal, non-metal. So now this one will be non-polar for sure. because oxygen and oxygen have an equal pull, equal electronegativities. If we looked at carbon, silicon, and nitrogen, carbon to oxygen is one step, nitrogen to oxygen, two elements away, one element away, and one, two, actually 3 steps and 1 down. That would be the furthest distance that you would have to travel to get from one to the other. And that's in general a bigger difference of electronegativities. So silicon oxygen would be considered the most polar. Now it depends on the compound. Right? These metalloids, sometimes silicon act like a metal and sometimes it acts like a non-metal. So just if we're only given the silicon oxygen bond, then we really don't know. Right? So we have to assume that it fits well in the definition. If it were silicon and 2 oxygens, that would definitely be ionic. Silicon dioxide, that's sand. But if it was silicon, oxygen, and then something else, then it could be behaving as a nonmetal. All right, 24. Which of the following atoms cannot exceed the octet rule in a molecule? All right. If we have to exceed the octet rule, that means the central atom has to have access to orbitals that can absorb. It has to have, if we have an octet, then we've got S's and P's, and we can have 2 here and 6 here. That would be your octet. So in order to exceed the octet, we need to have access to d orbitals at minimum. So which ones of these have access to d's? The ones that have quantum level 3, right? So silicon, phosphorus, sulfur would work. Oh, which of the following cannot exceed the octet? All right, so sulfur can do it. All right, sulfur is in the 3rd period, so it has 3 Ds available. Phosphorus has available. Iodine has available because it's down in 5s. Nitrogen. Yeah, nitrogen's only 2. Principal quantum level 2. So it doesn't have access to d orbitals. So nitrogen's your answer. That's the one that does not exceed the octet as a central atom. Which of the following has 0 dipole moment? We have an E, and we do have an E. All right, we have ammonia, nitrogen dioxide, PF5, SO2, and HCN. Okay. Ammonia. We've done ammonia before. I mean, if you start from scratch, you do the Lewis structure. And you get your electronic configuration. Then you get your molecular structure by covering it up and seeing, all right, do we have balanced? Right. The 2 things you need to determine dipole. Right. One is polar bonds or unpaired. See, not unpaired, non-bonding. Non-bonding electrons. That also fits in there. And 2 is geometry. Okay, so ammonia, we've drawn ammonia before. Right, it has lone pair up here. It has hydrogen in the back. It has hydrogens out here, here, and here. And that would give us the triangular base. So it's a triangular pyramid. And the bonds are polar in this direction. It also has the lone pair. So overall, it has a dipole like that. Okay. How about NO2? Let's go ahead and do this one the long way. Let's see. Valence electrons 5 plus 2 times 6. Yeah, it's 12. So that's 17. So we have nitrogen, oxygen, 2, 4 equals 13, correct? 2, 4, 6, 8, 10, 12. We have 1 electron left over. It goes right here. All right, so 3 groups. The VSEPR model says 3 groups is trigonal planar. So our molecule is going to look like this. Well, it's actually going to have a double bond on one side or the other. We'll just draw it one way for now. But we still have that one. This is one of the failings of the localized electron model. Is we have an unpaired electron. What do you do with those? Nothing. Right. All right, so nitrogen is more electronegative than oxygen, plus you have that lone electron. So its dipole is going to be like that. PF5. All right, so phosphorus has 5. 5 plus 5 times 7 is 35, right? So we have 40 electrons. And we have a P in the middle. And we have 1, 2, 3, 4, 5. That 2, 4, 6, 8, 10. So we have 30 electrons left. So if we have 6 around each one, 6 times 5 is 30. That's it. Right. And there are no lone electrons. So our structure here is going to be trigonal bipyramid. And that means perfect symmetry. Each bond is going to be polar toward the fluorines, but they're all balanced, perfectly balanced in this geometric figure. This is non-polar. Okay. And we found our answer. SO2 is going to be bent. Right? It'll be like this one. With some lone electrons. And HCN is linear, but it's going to be like that. It's going to have this and this. So that's polar. And this is bent. Let's see. S is same as oxygen. 3 times 6 is 18. So S O O 14. 6, 8, 10, 12, and then 2 up here. And actually, one of these is going to be double bond, either side. So we have to resonate. And that gives you an octet for everybody. But it's going to be polar like that. So this is the only non-polar one right there out of that group. Oh, we can use the lab today. We might be able to knock this one out, and then you won't have to come back on Thursday. Since everybody's either here or here, then we can make that decision at the end of the class, and I don't have to send anybody a message. 26. Okay. The hybridization of the central atom in xenon pentafluoride ion. Xenon. All right, ion. Okay, so this is going to be 8. That's going to be 7 times 5 is 35 minus 1 for that charge. Okay, so what's that, 42? I think. So we have xenon in the middle. We have 5 fluorines. Let's see, 2, 4, 6, 8, 10. So that's 32 left over. So that's 5 times 6, it's 30. So we have 2 electrons left over. They go right in. Okay, so what do we got going here? We've got 6 groups. Electronic structure would be octahedral. So we've got xenon in the middle. We've got let's see, square there. And where do the lone pairs go in an octahedral? Right, the apex. So we have lone pair up there, and we have fluorines here, 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 here. Okay, what was the question? Hybridization. So the hybridization we can do without that structure. All we need to know is how many groups. So it's octahedral with 6 groups. The hybridization has to be sp3 with D2. 1, 2, 3, 4, 5, 6. Yep. Okay. D2sp3. All right, 27. Which molecules have p orbitals that share an electron pair to create pi bonding? P orbitals. Oh, if we're going to create a pi bond, all you need is either a double or a triple bond, right? And all 3 of them have pi bonds. So that would be D, all the above. Right? What if, though, the question were, which one has equal bond lengths and bond energies for all the bonds? Only one. Right? That's the aromatic one. And we sometimes represent it by, this is benzene, like that, to show that all those double bonds are resonating. Let's see, we call that let's go blank. Conjugated. All 3 are conjugated into this aromatic system. It's a perfect, it's like a donut up above and below the plane that delocalizes electron density. When you can delocalize electrons, you get a more stable molecule or more stable bond system. And that makes all the bonds equal in length and strength. We can't say that about 2 and 3. They have unequal bond lengths. Now, number 2 has 3 of those bonds will resonate, but the other 3 will not. So that adds to the instability of that molecule. It exists, right? But it's not as stable. And then the 3rd one is probably, well, it's a toss-up whether it's more stable or less. It's probably less stable than the number 2. Now you're getting into organic geometry, and we're not going to go there. 28. A species has the following molecular orbital configuration. This substance is, okay, paramagnetic or diamagnetic with 1 unpaired, 3 unpaired. Okay. So let's see, we have sigma 1s, sigma star 1s, sigma 2s. Oh, I see it. It skipped down to the next line. Sigma. So this is 2, 2, 2. Sigma star 2s. Then sigma 2p and pi 2p with only 2 electrons in it. Everybody see that one? Okay. So these are all paired because you can only have one for each of the sigmas. But the pi's can have 2 bonds. And we're going to obey Hund's rule, which means 1 here and 1 there. Right? 2 unpaired electrons, which makes it paramagnetic. Which B would be the best answer for that then. Paramagnetic with 2 unpaired electrons. You have to understand, in order to answer this, all you have to know is that these guys are paired because there's only 1 orbital each. And these, molecular orbital, these have 2 molecular orbitals with, this is 2 degenerate orbitals. Stay there. Let's see. 29. Let's see. Which of the following contains the strongest bond? The best way to answer this one is to calculate bond order. So if we start at the top, we've got, and these should all be the same sequence of molecular orbitals because they're all dinitrogens. E. Oops. Yeah. There we go. So for this one, we're going to leave out the 1s sigmas. We're going to start with the 2s sigmas. And then the sigmas 2p's. And then the pi 2p's. It's reversed. Pi is first. Sorry. SP mixing. And then sigma 2p. And then we get pi star 2p and sigma star 2p if we need them. Okay, so this first one is N2. And we're going to count valence electrons only, which means 10. 10 electrons. So we have 2, 4, 8, and 2. Okay, and then we can calculate bond order. Okay, so bond order is 2, 6, 7, 8 minus 2 divided by 2, which is 3. Bond order 3. The next one is singly charged. Have 1 negative. Where does that extra negative go? Because that one's full. That extra negative has to go here. But got to go there. Which means now we have 8 minus 3 over 2, which is 2.5. That's weaker. These are the same. Next one, doubly negative charge. We're going to get 2 in this one. So now we have 8 minus 4 over 2, which is 2. Now D actually takes an electron away. We have 2, 2, 4, and 1. So now we have 7 minus 2 over 2, which is 2.5. And, oh, excuse me. There we go, plus a detail. Now we're going to take 2 away. That means 2, 2, and 4. and nothing there. So this means 6 minus 2 over 2, which is 2. Okay, so the strongest bond is neutral dinitrogen. It's a triple bond. And the weakest one, that's a toss-up. This one or this one. All right, number 30. Equal masses in grams of hydrogen gas and oxygen gas are reacted to form water. Which substance is limiting? Okay. So we need a balanced equation. We need hydrogen gas plus oxygen gas yields water. And for our purposes, it doesn't matter. Let's say it's liquid. Now we got a balance. So we got 2 oxygens here. We need 2 oxygens there. That gives us 4 hydrogens. There's your balanced equation. Now, equal masses of hydrogen and oxygen are reacting. Equal masses. So we have X grams here. We have X grams here. Okay. We could work this 2 different ways. We could either continue with our algebraic expressions using X and convert X grams into moles, or we could actually put values in there. Right? If we had, say, equal grams, let's say we have, all right, let's make it simple. Let's say we have 32 grams. It really doesn't matter, equal grams, 32 grams. Okay. So that would be 1 mole of oxygen gas, right? This would be about, let's see, 2 would be 16 moles. Okay. For every one of these, you need 2 of those. So for one of these moles to go over here, if we use up that mole, how much of this one are we going to use up? We're going to use up 2 moles, right? We have hydrogen left over, which is excess. That makes oxygen limiting. Okay. Oxygen gas is limiting. I think it's easier to use actual values. Okay. Let's see, 31. Um, 45.9 gram sample of metal is heated to 95.2 degrees and then placed in a calorimeter containing 120 grams of water at 21.6 degrees. The final temperature of the water is 24.5. What metal is being used? All right. For this one, we want to calculate the specific heat for the metal and compare it to our list. So remember, in a calorimeter, everything that happens in Vegas stays in Vegas. Everything in that calorimeter in terms of heat must be equal to 0. Right? We've left out the calorimeter calculation in here. So we really only have to calculate Q for the water plus Q for the metal. Okay. And in that case, Q for the water is going to be the mass of the water. Well, let's go ahead and do it like this. mass of the water times the specific heat of the water times the change in temperature for the water. Okay. And then for the metal, similarly, the mass of the metal times the specific heat of the metal, and that's what we're after right here, times the change in temperature for the metal. Now we can fill in our values. So the mass of the water was 120 grams. 120 grams times specific heat, 4.18. They're just using 4.18. That's joules per gram degrees C. And then change in temperature for the water, final minus initial. Final temperature is 24.5. Minus initial, 21.6 degrees C. Okay, that's the water term. Mass of the metal, 45.9. 45.9 grams. Specific heat of the metal and the change in temperature. Final temperature is the same, 24.5 degrees. Minus the initial temperature, 95.2 degrees. There we go. We got our equation set up. Now all I have to do is solve for that value right there and compare it to our table. All right. So let's see. 120. Oops. There we go. 4.18 and 24.5 minus 21.6. Multiply. So I get, for this term, 1454.6 joules, because grams cancel, degrees cancel. We're left with joules. So on this side, we get a value here, 24.5 minus 95.2 is minus 70.7 degrees C times 45.1 is minus 3245.1 times S. Yeah. Okay. Is equal to 0. So in order to solve for S, we've got to get the unknowns on one side and the knowns on the other side. So I think to get rid of the negative sign, we just take this one, put it over here. Now it's positive. 3245.1 and equals 1454.6. So SM is equal to 1454 divided by 3245.1. See, it's already, yeah. 0.448. 0.448 joules per gram. It looks like iron is the closest one to that one. So if you know how to do this calculation, then I could change those parameters and it could be a different answer. But you would know how to set it up. Let's see. Next, 32. Nitric acid was first prepared We've seen this one before. 1,200 years ago, by heating naturally occurring sodium nitrate with sulfuric acid to produce sodium bisulfate and collecting the vapors of hydrogen nitrate. Calculate the delta, the standard enthalpy for this reaction given the following enthalpies of formation. Okay. Now, is that equation balanced? Sodium nitrate plus sulfuric acid and sodium bisulfate plus HNO3 vapors. How do you collect those vapors? Any idea? You heat this stuff up. They probably used a retort. Call it. It's a thing like this, long neck. And then water, and the bubbles of hydrogen nitrate come out there, dissolve in the water. Okay, so we want to calculate delta H for this reaction. And we know the heats of formation. Let's see, is this balanced? Sodium, sodium, good. Nitrate, nitrate. Two hydrogens, one there and one there, and a sulfate. Okay, we're balanced. So how do we calculate this if we know the heats of formation? The heat of formation of the products minus the heat of formation of the reactants. Right? So, let's see, minus 1125.5 kilojoules is this one. Okay. And then nitric minus 135.1. 135.1. And then subtract sodium nitrate, saltpeter, minus 467.8 kilojoules. And then sulfuric acid, minus 814. Yes. There we go. Well, let's see if we come up with a same answer the key calls for. 1125.5, change sign. 135.1, subtract. And then we have 467.8 and 814. And I already multiplied this one times the negatives. So that's a positive value. Add it to this one. And I should get 21.2 kilojoules. Yeah, heat. That's the delta H. That's fairly simple. Oh, there it is. Okay. How about number 33? Fill in the table. Okay. All right, we have manganese 3 plus. Manganese 3 plus 55 here. We need the number of protons, neutrons, electrons, and atomic number. Atomic number. Mass number. And charge. Okay? Charge is easy. 3 plus. Mass number is easy. 55. Atomic number, we have to look that one up. So we look for manganese. Where's manganese? Fourth period, middle of the transition metals, 25. So atomic number is 25. That means protons, 25. Neutrons, 25 from 55. 30. How many electrons though? We have 25 protons, but we have 3 excess protons. That 22. Yep. So 25, 30, 22, 25, 55, and 3 plus. There we go. All done. Naming compounds, 34. Okay, FeSO4. Well, we know we're going to have iron and we're going to have polyatomic sulfate. All right, iron, sulfate. Type 1, 2, or 3? Well, it's not a type 3 because you got a metal and a polyatomic. So it's either a 1 or a 2. Iron could have more than one possible oxidation state or charge. So it has to be a type 2. That means we have to say what the charge is. So what is the charge? Well, if there's only one of these and one of those, and this is a 2 minus charge, this one has to be a 2 plus. Yeah. Let's see. Sodium. And what's that other thing? C2H3O2. Acetate. Sodium acetate. Type 1 compound, right? Sodium can only have one possible charge because it's an alkali metal. So that's it. We're done. Next one, silver and chlorine. Silver, chloride. Do we have to say what the charge on silver is? No. Silver is one of those transition elements that has a fixed charge. Silver, cadmium, and zinc. Yes. Silver, cadmium, and zinc have fixed charge. So silver chloride is it. Calcium. And our sulfate again. But that's an alkaline earth, fixed charge of 2 plus. One of these, one of those. We're done. And then this one, N2O3. That has nitrogen in it. Oops. Try that again. And it has oxygen in it. Oxide. But since they're both nonmetals, type 3 compound, we have to say how many there are. This is dinitrogen trioxide. Okay. Let's see, write the formula for, okay, it's just those two. Aluminum hydroxide. We got aluminum hydroxide, polyatomic ion. It has a -1 charge. Aluminum is fixed charge at 3 plus. That means we need 3 of these. ALOH3. Okay, don't forget the parentheses. And the second one, sulfurous acid. We know it's going to be an acid. Us's come from ites. So it'd be sulfite, SO3, 2 minus. That means we need 2 hydrogens. Okay, you don't have to write that in there. H2SO3. Now, technically, we should say this, but I'll cut you some slack if you just write the name in, write the formula in there. Okay, let's see. We're going to break away from the classroom so that I can correctly work this problem, number 36. I located the real problem with this one that gave me trouble in class, and I'm substituting this for that classroom experience because I found a problem with the data. That's why the answer didn't work. So I'm going to work it out again, this time using the correct component equations. All right, for 36, we want to use Hess's law. Hess's law to give us our target equation, which is calcium carbide solid plus water, two of these, and that should yield calcium hydroxide. Get us trouble here. Keep it from streaking. Aqueous and C2H2, acetylene. Gas. All right, so there's one of those, two of these, two of these. So this equation's balanced, but we want to calculate the enthalpy for this reaction. And of course, it's already given, but notice in your document, you'll probably see that this is 1/2. It should be 5/2. And if I had been paying closer attention, I would have noticed that a half of an oxygen is not enough to cover all the oxygens for the other side. So with 5/2 oxygen, now we have the ability to go at this from Hess's law. If we start with calcium carbide, that would be the first equation needs to be inverted. And that's all. It just needs to be inverted, placed in position. So we have calcium carbide here. Yields calcium solid plus 2 carbon graphite. And the value would be positive 62.8 kilojoules. I'm not going to write kilojoules in there because there's not enough room. Okay, so that takes care of this one. Now let's see. Let's skip water. I think that's what I did before. And go to calcium hydroxide. Calcium hydroxide will be the third equation. And it's correctly written with calcium hydroxide on the right-hand side and only 1 mole. So all we need to do is calcium oxide plus water yields calcium hydroxide in aqueous solution. And that's written minus 653.1. Okay. Well, that takes care of this one. And we keep that one, keep this one. Well, I'm underlining these because calcium doesn't appear anywhere up here. Graphite doesn't appear anywhere up here. And that way, I know which ones to keep and which ones should cancel out eventually. Now let's go to acetylene. Acetylene is the fourth equation. It needs to be on the right-hand side. That equation's on the left-hand side. So let's flip the equation, and that's all we need to do. So let's see. We need acetylene plus 5/2 of oxygen gas. And that value is going to be, the enthalpy will be change sign. So instead of 1300, we should have positive 1300. Okay. And we're keeping this one. Okay, so now we need, let's see, we've used the first one, calcium oxide. We need to use the second one to get rid of the calcium oxide. Calcium oxide on that side, we're inverting it. And on this side is calcium solid. Oops, I forgot to finish this one out. C2H2, 5. Okay, 2 CO2 and 1 water. There we go. Okay, now back to this one. Calcium and calcium oxide. Calcium oxide, yes, it'll get rid of that one. And we leave it just as is. Calcium plus 1/2 oxygen. And the value there will be the same as in the table. Minus 635.5. Okay. So that gets rid of this one. Here. Calcium. 2 carbons. That's still there, isn't it? Yeah. Okay. So now we need to get rid of the graphite. And that would be the very last one. Graphite's on that side. We need to put it on this side so it'll cancel. Graphite plus an O2 yield CO2. And that's written as is, minus 393.51. Okay, we've used up all the equations. 1, 2, 3, 4, 5. Now let's see. We kept this one. We've got 2 waters here. That's good. Calcium hydroxide is good. Acetylene is good. And one mistake. We need 2 graphites. 2 carbon graphites. Yeah, let's see. Where did I see that? There it is. It's the first one. That means this one has to be doubled. 2, 2, and 2. And this one has to be doubled also. So it's going to be 2, 0, 1 and 6 is 7, 18, 787. Okay. So now the 2 CO2s will cancel. Let's see. Graphite cancels. We've got 5 halves oxygens, which is 2.5 oxygens. So there's 2 of them. There's another half. Oxygens are gone. So we kept this one, canceled, kept that one, kept the waters, kept the acetylene, cancel. So now all we have to do is add up all the values. So we have 1, 2, 3, 4, 5 values to add up and see what the enthalpy for this reaction is. 62.8, 653.1 minus 1300 plus 635.5 minus 787.02 minus. Minus 712.8 kilojoules. Close. 713 rounded off. Okay, so that takes care of number 36 with the correct component equations. In your document, you'll probably have a circle around this oxygen because I couldn't understand why it came out wrong. And the reason it came out wrong was one of the equations was wrong, this one right here. So now that one's good. Moving on. But you get the idea. Hess's law. When it works, <clears throat> 37. Which of the following has the largest first ionization energy? Okay. First ionization energy. Ionization energy is lower left to upper right, correct? And if it's in the same group, sodium and rubidium are in the same group. So the higher first ionization energy would be above. That would be sodium. Uh, 38, which of the following has the largest atomic radius, nitrogen or oxygen? Those are neutral. So the atomic radius decreases from left to right. Why? Because of increasing nuclear charge. So the largest atomic radius would be nitrogen. Oxygen would be smaller. Consider the structure of glycine. This is an amino acid. Indicate the hybridization of each and how many bonds are in the molecule. Oh, and how many pi bonds. Okay, get the whole thing on there. All right, this is glycine. Let's see, we need, let's see. Draw it with you. Okay, there's your acid, amino acid. There's the acid. And here's the amine part. Okay. Amino acids, all of them have this alpha carbon. They have the acid group, and they have the amine group, and they have a hydrogen. And then this one is the variable. It can be any number, well, about 20 essentials. So you can have 20 different types here hanging off there. And when you string them together in a protein, this one from one amino acid bonds with that one from the other. So it's actually an amide bond, a string of amides. But because of the structure here, it's a special type of amide. It's a peptide bond. Just for future reference. Now to answer the question. Hybridization. Okay. This one has 1, 2, 3. So that's sp2. This one has sp3. And this nitrogen has this carbon, this nitrogen, and those two hydrogens like that. So this one is also sp3. sp2, 3, and 3. Okay. That's the tricky one. Knowing that you have that lone pair in there. Okay, how many bonds are in the molecule? Well, let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 bonds. How many pi bonds are in the molecule? Just one. Right there. There's another polyamide that was invented just prior to World War II, where it has the acid bonded with an amine. And it was developed by DuPont, a scientist at DuPont. His name escapes me for the moment. Carruthers. Sounds familiar. Anyway, up until that point, parachutes were made with silk. It was very light, very strong. And it's a protein, actually. It's an amide type bond. Well, this fellow from DuPont was playing with possible synthetic amide bonds. And he came up with nylon, which is like protein, but it's synthetic. And it's strong, very light, and solved the problem of getting enough silk to make parachutes because of where most of the silk came from, Far East. Right, Japan makes a lot of it, China made a lot of it, and they were kind of cut off. So solved that problem for us. Number 40. Oops, it's starting to get a little weak. Like this one. You're holding two balloons, orange balloon and blue balloon. The orange balloon filled with neon. Blue balloon filled with argon. The orange balloon is twice the volume of the blue balloon. And the orange is neon. The neon will be like this. And then the other one is argon, and it's about half the size. Okay. Let's see, this is orange. This is blue. Okay. The orange balloon is twice the volume because which of the following represents the mass ratio of neon argon in the balloons? All right. Here we can estimate. We don't have to be exact. What do we know if these are at the same temperature and pressure, standard temperature and pressure, say, same temperature, 1 equals 2, same pressure, different volumes. This volume is twice this volume. Okay. What do we know about the number of molecules? Well, in this case, atoms. Number of atoms in each one. If this volume is twice that volume, then the moles of this one equals twice the moles of that. All right? Okay. So now that we know that we have twice as many atoms here as there, the way to get at the mass is their molar mass. And argon is about 40, roughly. Neon is about 20. Yeah, it's about 20. So if we've got twice as many neons as argons, but the argons are twice as heavy, then the mass are equal, 1 to 1. Uh, 41. Start to give out too. They get a mustache here. Which of the following electron configurations is different from that expected? Okay. you're gonna get the differences in electronic configurations that we expect are gonna happen in one of two places. Transitions or what do they call them? Huh? Lanthanides, actinides, but there's a name for that. They call them internal transitions, I think. Yeah. So the representative elements are going to fall into line. That being said, we can say calcium is going to be fine. There's nothing wrong with calcium. The rest are transitions, so we have to look at those. So A is calcium, it's going to be okay. B, C, D, E. Scandium, titanium, vanadium, and chromium, right? Okay. We really only need to look at the d orbitals if we're in the transitions. That's where the difference is going to be. So for scandium, titanium, and vanadium, and chromium, all of them are 3Ds, right? Well, let's keep the S's in there also. They're going to be important. Okay. Right, now what would we normally expect for these? Well, the S's would be filled. And the D's would be, scandium would have 1, titanium 2, vanadium 3, chromium would be 4. Okay, we're talking about stability here. What are the most stable arrangements? There are two possibilities. D has 5 subshells. I mean 5 orbitals in this subshell. The most stable for that subshell and for the entire molecule, the entire atom, is either completely filled or half filled. Right. In order to get half filled, which is where we're headed here, we have to steal one from S. There we go. So that's the actual configuration for chromium, where you take one from S, put it in the D's, and that lowers the overall energy. So chromium is the one that's not standard. Different than expected. The other one would be on the other end, would be between with copper. Like copper would have we'd start off with 4s2 and 3d 9. But we take one of those, that, make that 10. That's more stable. Okay, so copper, I could put copper in there also, would be an oddball. Unexpected. That happens also with F orbitals. F can have 7 orbitals. So its most stable is going to have 7. If you get close to 7 singly occupied orbitals, or 7 with doublets, so you'd have 7 or 14, then you would steal from the S's to do that. All right, let's see, 41. Which of the following electron? Oh, we already did that. 42. Choose the molecule with the strongest bond. All right. Well, they're all covalent bonds, right? They're non-metal. So the strongest bond we would expect to follow, we need to know a couple of things. One is electronegativities, differences in electronegativities. And two, size. How close can you get those nuclei together? Carbon and hydrogen are pretty close, actually, in electronegativities. Hydrogen and oxygen, they're further apart. Right, so they're going to be stronger. Nitrogen and hydrogen, they're kind of between. So I would put, let's see, this one here, and nitrogen and hydrogen, and water in terms of strength of bonds. But HF is extremely high difference in electronegativity. So this HF would be a very, very strong bond. And that hydrogen is just a proton. So it can get really close to the fluorine. So for that reason, I would say that's probably the strongest one. Difference in electronegativity and the fact that that proton can get close to the fluorine. Because the fluorine is not that big. In fact, we know that fluorine has been shrinking as we go from left to right, right? So it's going to be a smaller atom anyway when it forms that bond. We're not running out of time, are we? Okay. Oh, is it getting bad outside?
Not here, but at home.
Oh, where's home? Oh, yeah. That's a different planet over there. Yeah, if you need to go, go ahead. Okay, let's see, how we doing? Oh, we're getting into short answers now. We're not far from the end. 43. 3 samples of solid substance composed of elements A and Z are prepared. Okay, substances A and Z. We don't know what their ratios are yet, their molar ratios. The first contained 4.31 grams of A, 4.31 grams of A, and 7.7 grams of Z. So this is A and Z. Okay, the second one had 35.9% A, and 64.1% Z. It was observed 3 samples. Let's see, first, second. Oh, okay. It was observed that for the third sample, 0.718 grams of A reacted with Z to form 2 grams of the third sample. Okay, so the ratio now is going to be 0.719 grams of A, and Z is going to be 2 minus that, because that's the total, minus 0.719 grams is Z for the third one. Show that these data illustrate the law of definite compositions. All right, definite composition simply says the mass ratio is the same, no matter where the compound comes from. All right, so what's the ratio of, let's see. Let's do Z to A. Z to A ratio. Let's do it this way. Z to A ratio by mass. Okay. So that'd be 7.7 divided by 4.31. That's 1.8, 1.79, sorry. 1.79. Here we can ratio just the percent because say we have a 100 gram sample. a 100 grams total sample would be 64.1 grams of Z and 35.9 grams of A. That's 1.79. And this one, we need that value, 2 minus 0.719 is 1.281 grams. That then is divided by 0.71715. Is 1.78. Pretty close, not exact, but close. Within experimental error, we show that the ratio, the mass ratio of Z and A are the same for each compound. That proves our point. Write the balanced equation for the combustion of ethanol. Okay, the way that question is written, the only thing you have is one reaction, one reactant. And for all combustion reactions with carbon-based compounds like this, C2, let's see, this is number 44. C2H5OH. Yeah. Combustion reactions are all reacted with oxygen. And they produce carbon dioxide and water, always. So to balance the equation, if we use the budget method, which is the most reliable, we have carbon, hydrogen, oxygen. That's it. So we have 2 carbons, 6 hydrogens, 3 oxygens. Over here, we have 1 carbon, 2 hydrogens, and 3 oxygens. Is that right? Yep. Okay. So where do we start? Well, we're going to hold this one out to last. That means we'll just start with carbon. So if we put a 2 here, that changes the oxygens to 4, 5. And hydrogens, we need 6 on that side. So we need a 3 here. That would do 6. That would also say 3 plus 4 is 7. Now we can use this oxygen to give us 7. So how would we get 7 out of, how do we make 7 from 3? Well, 7, if we do 7 halves, that will give us 7 oxygens. Okay. Oh, no, my mistake. What did I forget? I already got 1 oxygen over here. Right? So actually I only need 6. 6 plus 1. So 3 here gives me 6 plus 1 is 7. I didn't have to use the trick. And there's your balanced equation. So the trick to this one is knowing what a combustion reaction is, and then knowing what the combustion gives us as products. And the rest then is crunching numbers. All right. Let's see, what do we got next? 45. Photogray lenses incorporate small amounts of silver chloride in the glass of the lens. The following reaction occurs in the light, causing the lens to darken. So the light that hits the glasses takes the silver chloride and breaks it into silver ions and chloride ions. And you get a different, you get a more, you get a change in absorption spectrum. The enthalpy change for this reaction is 3 times 10 to the second kilojoules per mole. Assuming all the energy is supplied by light, what's the maximum wavelength of light that can be caught, that can cause this reaction? All right. So if the energy that's involved here is 3.1 times 10 squared kilojoules, and we've only got 1 mole in the reaction. So the delta H gives us actually 310 kilojoules. 310 kilojoules per mole. And the amount of energy required for that reaction would be 310 kilojoules. But we're going to have to, our calculation involves how many joules for each molecule. That's per mole, kilojoules per mole. We want joules per mole because of the way the equation is set up for calculating energy. So this kilojoules needs to be 310,000 joules per mole. Per molecule, we need moles on the top, molecules on the bottom. Right? 6.023 times 10 to the 23rd gets rid of moles and molecules. And that's all we need because we've already changed it to joules. So 310 divided by 310,000 divided by 6.023 times 10 to the 23rd is 5.147 times 10 to the minus 19th joules. Then we want to convert that to wavelengths. Well, we know this equation, Planck's constant and frequency, but we want wavelengths. So let's do it all in one fell swoop. We know that speed of light equals frequency times wavelength. Okay. So if we solve for that, then we have C over lambda. That means H times C lambda. Okay. So now we can calculate the energy. Right. We know what Planck's constant, I never can remember that, is no, that's not it. Oh, there it is. 6.626 times 10 to the minus 34. 6.626 times 10 minus 34 joule seconds. And then the speed of light is 2.9979 times 10 to the 8 meters per second. And then the wavelength is our unknown. And that's equal to the energy 5.147 times 10 to the minus 19th joules. So we needed that in joules because this is in joules. So if we solve for the wavelength goes on that side. And this one comes over here. So it's 6.626 times 10 to the minus 34 joule seconds times 2.9979 times 10 to the 8th meters per second divided by 5.147 times 10 to the minus 19 joules. That cancels the joules. Seconds cancel here. It leaves us with meters. So we got the right way. We got the right values. And that should be 3.858 times 10 to the minus 7 meters. And you'd either put, it doesn't specify the units of measure, so that would be acceptable. If we went to nanometers would be 10 to the minus 9th meters. So we need to make that 10 to the minus 9th. That means we need to store up 2 of these over here. So 386 Then. Or 380, yeah, 386 there. So that's the wavelength of light that the minimum maximum wavelength. In other words, the wavelength has to be that or shorter. Shorter wavelength would be more energy. So we have a minimum amount of energy or a maximum wave used. All right, this one looks familiar too. I think we're going to finish today. We don't have to come back on Thursday. Okay, 46. All right, we got 1, 2, 3, 4, 1, 2, 3, 4. What do we have? Go. So this one is hybridization, electronic geometry, and bond angles. And we have these three molecules, and we're given this one, both there and in the text. A has a hybridization of sp3. B has two more effective pairs of electrons around the central atom. So if this has two more pairs, that means it's D2sp3 hybrid. Molecule C consists of 1 sigma and 2 pi bonds. So it's 1 sigma bond and 2 pi's. Both of those pi's must be with the sigma because you can't have a pi without a sigma. And there's only 1 sigma. So both pi's have to be with a sigma. That means triple bond. And triple bond always is linear, sp hybridized. So the electronic geometry is linear here. This one is 2, 3, 4, 6. That's octahedral. And sp3 is tetrahedral. Bond angle, nominal bond angle for tetrahedrons, 109.5 degrees. That's it. Linear, obviously, is 180 degrees. Octahedral, it depends on how many molecules you have in there. But octahedral has this square in the center, and then it has something up here and something down here. So if you have atoms at both apexes, then you've got 180 degrees. Everywhere else around this central atom, no matter which way you go, is 90 degrees. So the only two possibilities here are 90 and 180. Okay? Balance the following equation. Ooh. Looks like it's going to be a challenge. Let's see, did I work it out? No, I didn't. Okay. All right. Number 47. I attempted to do in class, but I ran into difficulty and couldn't work my way out of it. What I originally wanted to do was to show you how to balance this redox equation using a two-step procedure. First, you set it up as you determine the oxidation states for all the elements in the equation. Then you see which ones were reduced, which ones were oxidized, and you set up a scheme for balancing the electrons first. Once you get the electrons balanced, then you proceed to the second step, which is our standard budget method. Okay, so I'm going to do this one in that format now in this insert. Okay, so we start off with, let's see, 47. Let me see if this one's better. KI, excuse me. Let me move those down. Like this. How about KI plus HNO3 yields KNO3 plus NO. I think I'm going to run out of room. Plus I2 plus water. Okay. Well, let me see. I can shift those over some. Let me try that again. Ki plus HNO3. Ki plus HNO3. And then KNO3. And then plus NO. And plus I2. And plus H2O. So first thing you do is find the oxidation states for each of the elements. You'll also notice that nitrates here and nitrates there, but there's also a nitrogen compound over here. So this one was broken up in the process. That means we have to balance every element separately. But first we want to do the oxidation states. Right? Alkali metal, halogen, hydrogens, oxygens, -2, -6. That's a -6 and a +1, which is a -5. So this is a +5. And this is also a -2, +5, and a +1. This one's a -2 and a +2. That one's a 0, -2, and a +1. So those are your oxidation states. Now we can see that iodine's a 0. Over here it's a -1. So if we draw our tie line from here to here, we see that the iodine must have lost 1 electron for each iodine. It was oxidized, lost 1 electron per iodine. And one of these nitrogens over here, it had to gain 3 electrons per nitrogen. Okay. Now, if we set this up for 2 here, right, times 2 equals 2 electrons, that takes care of this discrepancy, 2 here and 2 here. This one is only 3 electrons. So remember, the best way to balance an even and odd is cross multiply. So we're going to take this 3 times here equals 6 electrons, and 2 times this one equals 6 electrons. Now, how did we get that 3? That 3 has to be multiplied by this one and this one. So this is a 3, and this would be a 6. Like that. And to get this one to be 6, we actually need 2 there and 2 there. Okay, so now we have the electrons balanced. From now on out, we're going to use the budget method. Okay. All right. So we've got, let's see, potassium. Let's see, maybe I'll put it over here. Potassium, iodine, hydrogen, nitrogen, and oxygen. Okay, potassiums. We have 6 to start with here. We have 6 iodines. We have 2 hydrogens, 2 nitrogens, and 6 oxygens. On this side, we have 1 potassium. We have 6 iodines. We have 2 hydrogens. We have 1, 2, 3 nitrogens. And we have 3, 4, 5, 6 oxygens. Okay. Let's see. Well, let's just start at the top. 6 potassiums. If we put 6 here, that will give us 6 potassiums, and it changes the number of nitrogens for 1 as 6, 7, 8. Now we have 8 nitrogens. Okay. And we have 18, 19, 20, 21 oxygens. Okay. Now let's see what else. Come over here and fix the nitrogens on this side. So we need 8 nitrogens here. That means 8 there. So now we have 8 hydrogens. And we have 8 nitrogens and 24 oxygen. Okay. Then we come over on this side. Let's go ahead and fix the hydrogens. Hydrogen only occurs in one place. So we need 8 hydrogens on this side. That means 4 here, correct? So that's 8 hydrogens. And 4 oxygens, 5, 6, and 6 and 18 is 24. 6, 6, 8, 8, 24. Now we're balanced with 6, 8, 6, 2, 3, and 4. That's how you use a hybrid method. The redox method first to balance the electrons, and then follow it up with the budget method. The next one, I started off with that answer. The question asks, one of the major commercial uses of sulfuric acid is the production of phosphoric acid and calcium sulfate. The phosphoric acid is used for fertilizer. The reaction is calcium phosphate plus sulfuric acid yields calcium sulfate plus is that right? Oh, it must have been a different problem. Yeah, there was a different problem before. Yield, calcium sulfate, and phosphoric acid. But this, and what mass of commercial sulfuric acid at 98% by mass must be used to react completely with 100 grams of calcium phosphate. This is not grams, right? We noticed that in the classroom, right? That was accidentally brought over from the answer to this one. That was correct, actually. So what we need to do is determine what is the value for the mass of sulfuric acid, 98% sulfuric acid, that will give us that will completely consume 100 grams of calcium phosphate. And let's pause for a moment. Let me do a quick calculation. This may not be the one I had trouble with. I think it was. I'm going to do this one also. Number 48. All right. We're given the balanced equation. So calcium phosphate plus sulfuric acid yields calcium sulfate plus phosphoric acid. Okay. Now we're given 100 grams of calcium phosphate. Okay. And we want to know how many grams of 98% by mass sulfuric acid will be required. This is a stoichiometry problem, and all you have to do is first, you can't go anywhere in this equation without moles. So we have to change this to moles. And the calculation of molar mass for calcium phosphate is right here. 3 times 40.08, 2 times 30.97, and 8 times 16 for the oxygen gives us 310.18 grams per mole. So we're going to take this 310.18 grams per mole. Excuse me. Let me make some room here. Grams needs to be on the bottom, moles on the top. So 310.18 divided into 100 equals the number of moles of calcium phosphate that we have to react. And that's 0.3224 moles. Okay. So now we can find out how many moles of H2SO4. This is moles of calcium phosphate. Now we have to multiply that times our conversion factor for calcium phosphate on the bottom and sulfuric acid on the top. And the ratio is oh, excuse me. 3, 3, and 2 is 3 to 1. So this should be 3 and that should be 1. So all I have to do is multiply that value times 3. And that gives me 0.9672 moles of H2SO4. Now that's pure 100% H2SO4. So in order to convert that, we need to convert this to mass first, because this ratio is mass to mass. So this has to be converted to mass. So the mass of H2SO4 is given up here, 2 times right there. Right. Okay. 2 times 1.01 for hydrogen, 1 times 3206 for sulfur, and 4 times 16 for 4 oxygens. And that should be 98.08. Okay, so these two times each other will give us the mass of sulfuric acid. Which is 94.861 grams. Okay. Now I'm running out of room, so I might be able to do it down here. Let's put it down below. So what I need to do now is convert this 94.861 grams of pure H2SO4, and the conversion factor is H2SO4 plus so many grams of solution, this 98% solution. So we only have 98 grams of H2SO4 for every 100 grams of solution. And that will cancel this and gives us the mass of the solution. So I get 96.8 grams of the 98% solution. So that value should be 96.8 should be up here. Grams of solution. There we go. Okay. Let's see if we can make sense of this one. 48. One of the major commercial uses of sulfuric acid is the production of phosphoric acid and calcium sulfate. Phosphoric acid is used for fertilizer, yes. The reaction is calcium phosphate is the way the mineral is mined. And sulfuric acid converts it to calcium sulfate and phosphoric acid. What mass of concentrated H2SO4 must be used to react completely with 100 grams of calcium phosphate? Well, that's not. How'd that answer get in there? That doesn't make any sense. That shouldn't be there. That's not mass. That's a formula. Okay, we need the balanced equation first, which we have. Calcium phosphate. Yeah. And then 3 sulfuric acid yields 3 calcium sulfate plus phosphoric acid. 2 of those. 2, 3, 3. Okay. 100 grams of calcium phosphate were given. 100 grams. And this is 98% by mass, I think. Yeah, by mass. So this is 98. This would be grams per 100 grams. And we want to know what mass of this must be used to react completely with 100 grams of calcium phosphate. Okay, we're going to need to convert this to moles because we can't compare the two unless they're moles. So we need 3 calciums, 40.08 for calcium, 2 phosphorus, 30.97, and 8 oxygens, 16. Let's see what that is. That's 310.18 grams per mole. All right, so we can convert this to moles. Oops. Like. Yeah. Oh, no, it had 2 zeros. 5 grams. And we will convert that to moles. So this is 310.18 grams per mole. Which is 0.32. See, 5 significant figures. 32239 moles of calcium phosphate. Okay. Now we can find out how many moles of sulfuric acid are required. Right. Conversion factor would be what? Calcium phosphate's on the bottom. 1. Calcium phosphate. And 3 sulfuric acid on the top. So 3 times that value is 0.96718 moles of H2SO4. Then we'll convert it back to mass of pure sulfuric acid. We haven't taken into account that impurity yet. So this has to be multiplied by the molar mass of sulfuric acid, grams per mole. Sulfuric acid would be 2 times 1.01. Sulfur is 30.97 and 4 times oxygen. 16. Is 96.99 grams per mole. 96.99 grams per mole. This equals 93.807 grams of H2SO4. Right. Now we have to convert. Right. So if this is grams of pure sulfuric acid, then the conversion factor is pure H2SO4 per grams of pure per 100 grams of solution. So this is 0.98. Oh, sorry. 98 grams of pure per 100 grams of solution. That's what that means. Okay. So, 100 times that and then 98 divided. So we get 95.72 grams of solution. Well, I didn't come very close, did I? Oh, wait a minute. That's not all of it. There we go. 96. How'd I get 95? Must be a rounding error. Let's see. Yeah, there's a potential rounding error there. There. 967. Oh. I think I did something wrong here. H2, 2.02. Sulfur. 30.97. And 64. 96.99, that's right. Okay, that's a mistake. 9808 H2SO4. 4 times 16. 1 times sulfur. And 2 times hydrogen. Okay, that's a mistake. That's wrong. It should be 95.72 grams of solution. Oops. 72 grams. Okay, where's my save? Oops. Save that. Should be able to save it. Maybe it won't let me save while I'm sharing. Okay. What's this one? 49. We go on time. 3 o'clock. We're good till 3:50. Okay. We should be able to finish.
I think you copied the answer from 49 to 4.
I'm sorry?
I think you copied that answer from 49 to what are you asking?
Oh, okay. Yeah, that's why it happened. Okay, this is going to be molecular formula. All right, y'all remember how to do that one? 49. We have to find the empirical formula first, and then we need a molar mass for the actual compound. So ethyl butanoate is our compound, and it has carbon. Let's see, compound containing only carbon, hydrogen, and oxygen. Combustion of 2.78 grams of ethyl butanoate. 2.78 grams of the compound is combusted in oxygen, correct? And it forms 6.32 grams of CO2. CO2, 6.32 grams, and 2.58 grams of water. Okay. Now, which one's missing? Well, carbon, hydrogen, and oxygen, but we combusted it in pure oxygen. So we can't determine, oxygen has to be determined indirectly. All right. How much of this is actually carbon? So if we want that, we need the percent carbon, which would be 12.01 would be carbon. And then 12.01 plus 32 for the oxygen would be the fraction of carbon in that compound. So we multiply this one times 0.273, and that will be the grams of carbon. 1.72 grams of carbon. And this one would be, hydrogen will be 2 hydrogen, and then 2 hydrogen in the denominator and 1 oxygen. That'd be 0.112. 0.112 times 2.58 is 0.289 grams of hydrogen. And then the oxygen, that's hydrogen, oxygen would be equal to 2.78 minus these two. Right? So 2.78 minus 1.72 minus 0.289 equals 2.78 is 1.00 grams of oxygen. And let's see if that adds up to the total. Let's see, 9, 10, 0. Let's see. Well, do that right. Do that again. 2.78, 1.72, and 0.2. No, it's wrong. Just didn't look right. 771. Now we're talking. So that's 10, 8. Yep. And then carry the 1 to 9, 10, 7, carry the 1. That's it. Okay, so that's the mass of each in this compound. All right. We've got grams, so we can convert this, each one of these, to their number of moles and do the ratio of moles. All right. 12.01, 1.01, and 16. One 1.72, 12.01. So this is 0.143 moles of carbon. And 0.289, 1.01 is 0.286 moles of carbon, hydrogen, and oxygen, 0.771. 16. So this is 0.482 moles of oxygen. Now we need to get whole number ratios. Smallest one in here is 0.143. So if we divide by 0.143 on each one, the ratio will be the same. We'll just be inching toward whole numbers. All right, that's 1. That looks like it's going to be 2. Yeah, exactly 2. And then 0.482 divided by 1.43 is 3.37. All right. So how do we get rid of that third? We multiply by 3. Now we're getting closer to estimation rather than exact numbers. This is close to a third. So if we multiply by 3, we get 3 here, 6 here, and 9 plus 1 is 10 there. So our empirical ratio is C3, H6, and O10. And that's going to be multiplied by some factor. And then the molar mass is between 100 and 150. So let's find out what the empirical mass is. 12.01 times 3 is 36.03, and then 6.06 for the hydrogens, and then 10 times 16 is 160. Is 202. That's not going to work out at all, is it? Molar mass suggested is between 100 and 150. Okay, we're still not lost. Except, okay, that looks okay so far. 361. Oh. How did I end up with that? 0.77. Oh. That's where the mess came. My decimal place is misplaced. 16 into 0.771. Yeah. 0.0482. All right. Let's start over again. This is the smallest one, 0.0482. There we go. This one's 1. This one is about 6. And 3. And this one's 3. 361. Now we're talking. Okay, let's try that again. 12.01 times 3, 6.06, and 16. That's 58.09. Okay. If n is equal to 1, we're not close enough to 100, between 100 and 150. Times 2 puts it pretty close in the middle. So if n equals 2, then our value here is 116. That's it. So our formula is C6H12O2. Oh, that's it.